Intro to cycles. A cycle is a series of thermodynamic processes that returns a system to its original state. Here I'm going to give you some vocabulary. I'm sorry about that. So first of all, isentropic means constant entropy, isobaric means constant pressure, isochoric constant volume, and isothermal constant temperature. Here we're going to have the different cycles that we'll see today. We're going to have a heat pump and refrigerator cycle that works with water at R134. We're going to have a Carnot cycle, which is the ideal cycle, ideal efficiency. We'll see it. We'll talk about that later. The Rankine cycle, which also works with water in R134A. And then the Otto cycle and the Brayton cycle, that's going to work with ideal gases.
The refrigerant and heat pump cycles. They're cycles that we use every day on our daily basis, such as cooling and heating systems. We have a graph and a diagram showing what's going on around here. At 1, we have a saturated vapor going into the compressor with a low pressure, and then when it gets to 0.2, it comes to high pressure. Process 1 to 2 is an isentropic process, and as you can see, we have work going in. From 2 to 3, we have isobaric process, which pressure is constant, and the condenser releases heat, as you can see. When it gets to 3, it becomes into saturated liquid before entering the valve. After entering the valve, the pressure goes down, and we have work leaving from point 3 to 4. From 4 to 1, it's an isobaric process again, pressure is constant, and we have Q that's being added through the evaporator.
And now we move on to the Carnot cycle. Within the Carnot cycle, there are 4 main components: a pump, a boiler, a turbine, and a condenser. Beginning at the pump, the working fluid undergoes an isentropic process to pressurize the fluid before it moves on to the boiler, where it undergoes an isobaric heat transfer in order to vaporize the working fluid and transform it into steam. This steam is then moved on to the turbine, where it undergoes an isentropic expansion to generate work at the expense of the fluid, at the expense of the steam's pressure and temperature. The steam mixture is then moved on to the condenser, where it undergoes an isobaric compression to transform it back into the original working fluid. This is the ideal Carnot cycle. However, in reality, we can't actually obtain this. More often than not, we use what is called the Rankine cycle. The only main difference between the Rankine and Carnot cycles is that in the Rankine cycle, it begins at the pump as a saturated liquid before being transformed into compressed liquid, before isobarically increasing in temperature to then be boiled and transformed into steam. It is for this reason that the Rankine cycle is used in the real world rather than the Carnot cycle.
We have the Otto cycle. So the Otto cycle is the thermodynamic cycle that best represents what we see in a car engine, hence the word automobile. So we're going to start here at state 1, which goes to state 2 by constant entropy. And this is where the work is going to come in, since the piston has to come down. Then, after the piston comes down, there has to be a spark ignition for the piston to go back up. So here's when we're going to have the Q in, the energy going in for the spark, and this is going to be done at a constant volume process, obviously. And then from state 3 to 4, it goes back to, the piston goes back up, and that is done by constant entropy. That's where the work is going to come from. After that, we have from 4 to 1, which is just going back to its original state, and that's when the energy is going to come back out. About the Brayton cycle. The Brayton cycle is the most widely used method for propulsion for airplanes. So here we usually work with air, but we can also work with we usually work with air and ideal gases. So here we start at state 1. It goes through a compressor. A compressor here we're going to have work in, and it's going to be an isentropic process to get to state 2. At state 2 we're going through a combustion chamber. Here we're going to have heat going into the system, and it's going to be an isobaric process, constant pressure. So we get to state 3. From state 3 to state 4, it's going to go through a turbine. We're going to have work out the system, and it's also going to be an isentropic process. You can see here from 3 to 4. Then from 4 to 1 back, it's going to go, from 4 back to 1, it's going to go through a heat exchanger. Here we're going to have heat going out of the system, and then the fluid goes back to its original state. Many different uses for the cycles. And this is going to be very important for us to understand for this thermodynamics class. Good luck this semester, guys.